It's a pleasure to speak points on rational normal curves and the ABCT variety.
Thank you for the introduction. It's a great pleasure to be here and speak about the ABCT variety and points on rational normal curves. This is joint work with Daniele Agostini and Lakshmi Ramesh. The work is not yet on arXiv. We want to upload after we finish a round of internal review, but you can see the draft and the slides on my personal webpage. Okay, so let's start by taking a smooth quasi-projective variety X. We take a line bundle on X and consider a linear system. And for each global section of L on X, we can consider its vanishing locus. And since scaling, the section will not change the locus, we will identify the family of the vanishing of a section with the projectivization of V. We will make the assumption that a general divisor in this family is reduced and irreducible. We define the point configuration space X to the n of V as a subscheme of the nth power of X, given by the condition that the endpoints lie on some common divisor in our family. Our first theorem says that this point configuration space with its natural scheme structure is reduced, irreducible, and Cohen-Macaulay, and its codimension in the nth power of X is as expected. This was first discovered by Caminata, Moon, and Schaffler last year, where they considered the special case when X is projective R space and V consists of all the degree D forms. So they're considering the point configuration for endpoints to lie on some degree D hypersurface in the projective R space. But we realized that we can adapt their proof and get a more general statement, which will be useful later. So we will apply this theorem for the case where X is actually an affine space. Next, let me define the Veronese maps on the Grassmannian. So we take n to be some large enough number, and we define the Dth Veronese map on Grassmannians by starting with the Grassmannian of K-planes in n space and map it to our Grassmannian for larger dimensional planes in still n space. And what this map does on matrices is that I take each column and then I exhaust all the degree D monomials in the column entries. And we put all the columns together to form a larger matrix with more rows, but the same number of columns. And what one can see that if you let some invertible matrix GLK act on the left of here, then on the image, you will be acting by the Dth symmetric power of some invertible matrix, which will also be invertible. So then this map between matrices gives you a map between Grassmannians. But this is not everywhere well-defined. For example, it's not well-defined exactly when the resulting image matrix does not have full rank. So we only get a rational map, and we denote the degeneracy locus of this rational map to be ZD of K, N. And this is this comes with a natural subscheme structure, and we can show that this subscheme is reduced irreducible in Cohen-Macaulay, and furthermore, its expected codimension in Grassmannian Kn is as expected. And the way we showed it is basically by passing to the standard affine charts on the Grassmannian Kn and then apply the previous theorem. So finally, let me introduce the main object of study, or at least this was our original motivation. So we consider those varieties called ABCT varieties. They were first considered by Arcani, Hamed, Bergeli, Cachasso, and Trinka to study tree amplitudes in Witten's twistor string theory. And for us, we'll just take the definition to be the Zariski closure of the image of the Dth Veronese map on Grassmannian 2n's. So this will be a subvariety inside Grassmannian d plus 1, comma n. And we will do the special case where d equals 2. So we will have a subvariety inside Grassmannian 3n, which is the closure of image of a rational map from Grassmannian 2n. And the reason why we like the d equals 2 case so much is because in this case, the variety, the ABCT variety actually agrees with the degeneracy locus. And for higher k, vkn will be strictly contained in the degeneracy locus, but they will not be equal. And this proposition is not so complicated to show once we know that the thing on the right is irreducible and has expected codimension, because we just need to show that dimensions match and then show one direction of containment. And as a corollary, we know exactly what the homogeneous ideal in the Plucker coordinates will cut out the ABCT variety as a scheme. And finally, let me discuss the computation of the fundamental classes of V3n. So we have this recursive formula giving a sequence of symmetric functions in 3 variables. And the claim is that those symmetric functions will give the fundamental classes of V3n up to a shift. And this formula basically says that we take Fm equals 0 for negative m, and for non-negative m, we can write each Fm in terms of the previous 3 terms. And just to show you some examples, here we have the first 5 symmetric functions where Fm will have degree n, and they will give the classes of V35 through V39. And you can use Macaulay 2 to easily compute the classes of V3n up to very large n. And as a corollary, so here, if we look at coefficient, so if we look at the Schur function expansion of Fm and take the coefficient in front of Sm, the Schur function indexed by a single row, then those numbers are 1, 4, 11, 26, 57. Those happened to count the number of permutations with exactly 1 descent. So this is the corollary that I'm showing here. And this is an example of a more general phenomenon discovered by Kashazo, He, and Yuan. So in their 2013 paper, they counted the number of solutions to some scattering equations. And let's recall from multiple previous talks that we have the spinor helicity variables lambdas and lambda tildes. The lambdas will give us a 2-dimensional subspace in n space. The orthogonal complement of the lambda tildes will give us a codimension 2 subspace containing the 2-dimensional subspace. And it turns out that any set of solutions to the scattering equations will give a witness for some k-space in the ABCT variety Vkn to contain the 2-dimensional subspace and be contained in the codimension 2 subspace, which is exactly the intersection between the ABCT variety with some generic Schubert variety. And in the special case where we have k equals 3, we want to look at the Schubert variety indexed by a single row. So originally they used the technique of a soft limit to show this result, but our approach is entirely algebra geometric, and we have the full fundamental class instead of one intersection number. And let me briefly talk about a sketch of the proof. Essentially, what we have done here can be generalized to all zkn. But the k equals 3 case is the only case where it agrees with the ABCT variety, and that is what we will do here. So we will realize Z3n as the degeneracy locus of a map of vector bundles then Porteous formula can tell us that its fundamental class will be written as determinant in the Chern classes of a vector bundle. Then we write the Chern classes as elementary symmetric functions in the Chern roots, and then use the Phong combinatorics of theory of symmetric functions and get our recursive formula. So that's all. And I wish to thank my advisor Thomas Lam for introducing this problem to us and the meaningful discussions that we had. And we want to thank Bernd Sternfels for putting this wonderful team together.
Very nice talk. We have plenty of time for questions. Yeah.
So the other coefficients in the Schur class, the expansion of the slip, do they have a nice interpretation?
Not that we know of.
Exactly.
So you mean those
23, 63,
you didn't realize any interesting.
Is it clear that they are positive?
Yes, because so this is the fundamental class of some variety, and each coefficient is the intersection number with some generic Schubert, so they are positive.
For this formula, you have some bundles, you need some global generation of those bundles.
Sorry,
The formula that you give, that you use to get this thing. Yeah, theme 2 of U check. So I guess theme 2 of U check is globally generated. What's the question? Sorry.
So are you asking whether
It is globally generated. Okay.
whether those two bundles are globally generated?
Yeah.
Yes, yeah. So we have the trivial bundle, and we have second symmetric power of the canonical dual, the dual canonical.
Any more questions?
Yeah, so here you're really using the fact that E3n is equal to this degeneracy locus.
Yes.
Can you compute the class of the degeneracy locus in general?
Yes.
I see. Okay.
So we have so we can have an analogous result for Z2 Kn for any Kn. Yeah.
Any more questions? Okay, if not, let's try the speaker again.